Today, I'm going to talk about joint embedding predictive architectures. So the acronym would be JEPA. And I'm going to present two papers, actually, I-JEPA and V-JEPA. I-JEPA was published in last year, and V-JEPA was published this year. The first one is about self-supervised learning on images. And the second one is applying the same idea, the same architecture, but to videos. And this is mostly from work from the FAIR group at Meta. All right, so I'll first go over the I-JEPA paper. So the paper starts by sort of a taxonomy of self-supervision methods. And the two main categories of methods that most people are familiar with are invariance methods, and what they call invariance methods, and generative methods. And so in this table, I sort of contrast these two. So in the first row here, I provide an example of what that architecture looks like. So for invariance methods, typically you start with an image. So here you have this little cat, and you create different views or data augmentations from that same image. So on the left, you go black and white. On the right, I forgot what that's called, but you sort of increase the contrast or something. But it's the same image. So those are positive pairs, and then they go through the same encoder. And then at the end of the day, you want to maximize agreement between the representation of those two different views of the same image. In terms of generative methods, this is the diagram from the MAE paper, I believe. So here the idea is, instead of using handcrafted data augmentation techniques like the ones here where you go black and white or you increase the contrast, here you simply mask parts of the image and then you sort of reconstruct that in the pixel space. If you want to represent this architecture in a more abstract diagram, so that's the next row in this table. The invariance methods can also be described as joint embedding architectures. So you have the two encoders here, the X and Y correspond to the different views of the same input. And then you try to minimize the distance between the embeddings of those two inputs. So that's the joint embedding part of the name. In terms of the generative architecture, it looks more like this. So you have an X and a Y again. So X would be the masked input. It would correspond to this image of is that a flamenco? And then the Y would be the uncorrupted image. So you encode the corrupted image. And then with an additional information here represented by Z, you're going to decode the embedding into the pixel space, back into the pixel space. So after the encoder here, you're sort of in the embedding space, and then you decode back into the input space, which would be pixels if it's an image. It would be, I don't know, text if it's text. And then you try to minimize the distance here. The Z, what corresponds to the Z here would be the mask tokens, as well as the positional embeddings for those masks. All right, the third row here, the third and fourth row are sort of criteria to evaluate those two types of methods, the invariance methods and the generative methods. And typically you can assess them in terms of semanticness. It's not a great word, it's not a made-up word. And in terms of generality, in terms of what I mean by semanticness is whether the embeddings from those methods are high level or low level. And what does it mean to have a high level representation or low level representation? Typically, you can think of it as if you can easily adapt the model to a particular domain, because we're talking about pre-training here. So pre-training is sort of agnostic task. Eventually, you want to take a pre-trained model and do something with it useful. So you adapt it to a domain. So semanticness is how easily you can apply, or you can adapt your model to a specific domain. And so you can do that with linear probing. The term, I didn't know what the term linear probing before reading this paper, but basically this just means you freeze your backbone and then you add a very simple linear head, and then you just fine tune the head. So that's what they call linear probing. So that's one way. If you can easily do that, that means you have high level representation of the for your embeddings. Another way of thinking of it is how quickly you can do transfer learning after you've pre-trained your backbone. So typically invariance methods have high semanticness. This is all relative. When I say low semanticness, it doesn't mean in absolute it's low. It means relative to the other method, meaning the invariance method in this case. The generative method have a lower semanticness than invariance methods. So why do I say that generative methods have low semanticness? Typically is because a lot of the model capacity in these approaches is dedicated to low-level details due to the fact that you want to reconstruct things in the input space. So you want to eventually decode your embeddings back into pixel space. And so for that, the representation of your embeddings after the encoder sort of needs to capture a lot of low-level details. And so you sort of lose in semanticness in that way. The second sort of way to assess those two methods is generality. It's sort of related to semanticness. Maybe there's a lot of overlap here, but what I mean by generality is that you have similar adaptability across domains. So you may have good semanticness or high-level representation for a specific domain, but having high-level representation across multiple domains, that's what I mean by generality. And the other sort of criterion for generality is that you can use similar methods across modalities. So in that criterion, the invariance methods score low because here going black and white as a form of data augmentation works for images, but it's nonsensical for audio, for instance. However, masking things is a very general method. And so you can use that method for image, video, text, audio. It's a very general method. And then in terms of adaptability across domains, again, the invariance methods score low here because this is more like empirical. We've noticed that when the downstream task or the domain that you're targeting is image classification, it works better with some types of data augmentation. So maybe cropping works better for data classification. But another kind of data augmentation would score better for a downstream task that is instance segmentation. So it doesn't really, it's not as general, essentially. And finally, these augmentation techniques, like I said, do not port over to other modalities. So audio, for instance, you would have to completely reinvent the invariance method. And in contrast, generative methods score high for generality. So this is sort of the literature review for self-supervision in one table. And the question that this paper asks is, could there be another method, another set of methods that score high in both semanticness and generality? And this is what the paper claims that's what JEPA does, essentially. So JEPA would be high in semanticness and high in generality. I'll go obviously into the details a little later, but this is sort of the overall architecture. The idea here is that you're doing, instead of predicting or reconstructing your target in the pixel space, you reconstruct it in the embedding space. That's the key thing in JEPA. And that's why it's not called a generative method, because you're not generating something concrete like an image. And so it's not generative in that sense. It's a joint embedding architecture, but it's also predictive. So let me try to go through this diagram real quick. So here you have the image of a little dog, I think. And you also have an X and a Y that are related to each other. So here the X would be sort of part of the image, and the Y would be a few other parts of the image here. So you would encode, so you're transitioning into the representational space or the embedding space here. And then you have a predictor that takes those embeddings and tries to predict not the actual image, but its embedding representation here. So the targets are also encoded, and then you're trying to predict the target embeddings from the context embeddings here. I'll go into more details over that in a second. Again, in a more abstract diagram here, same idea. You have the X and Y, and then the Z here is again the mask tokens and the positional encodings for the target. They call them blocks here that you want to predict. And you minimize some kind of distance, but in embedding space as opposed to in pixel space here. And the reason why it's high in semanticness, well, the reason it's high in generality is for the same reason that the generative methods score high in generality. But the reason why JEPA scores high in semanticness is because it doesn't have to dedicate model capacity to low-level details to reconstruct things in pixel space. The model has the flexibility to sort of eliminate irrelevant or unpredictable pixel-level details because you're operating in embedding space. By the way, feel free to stop me if you have any questions or if something is not clear. Yeah.
For this encoder, are they output the target is the feature vector itself or the probability to sample from the the features? Is it variation encoder or just a basic regular encoder?
It's just a regular encoder. So these are just embeddings here for those tokens. And I'll explain what I mean by token here. I'm sure you guys are familiar, but just in case. I'll go into more details in a second about that. I think it will become clear. This is a very high level table here. In this table, I contrast a little more these two columns, essentially, the invariance methods and JEPA. Invariance methods, alternatively, we call them joint embedding architectures. So that's GEA here, JEA. Again, this is the same diagrams. I just added here that the way you obtain X from Y is through some kind of handcrafted data augmentation, whereas here it's through some kind of masking. Again, Z here corresponds to mask tokens and positional encodings. But otherwise it's the same diagram. Again, the last function, we operate in input space or pixel space for joint embedding architectures, and in embedding space for joint embedding predictive architectures. The examples that we feed the model need to be both positive and negative for invariance-based methods, and that's to avoid the problem of representational collapse. So basically, if you only train a joint embedding architecture with positive examples, it collapses into a trivial solution. And so the way you avoid that we found sort of empirically is to mix both positive example and negative example. A negative example would be here you show a cat and then here you show a dog, let's say. So that would be a negative pair. Yeah, and the other main, oh, and for JEPA, you only show positive examples. You don't need negative pairs here. Because it's just a completely different approach. It's the masking approach. Another thing about the examples is that the positive examples come from domain-specific handcrafted augmentations. So that's what I meant here when I said that some augmentations work better when the downstream task that you're targeting is image classification. But if the downstream task is more instance segmentation, then you're going to use different types of augmentations. So that's what I mean by handcrafted domain-specific augmentations. As opposed to that, in JEPA, the positive examples come from domain-agnostic general token masking method. So yeah, that's thing speaks for itself. Domain-agnostic meaning there is no handcrafted augmentation, you just mask. So it's a very domain-agnostic method. The goal for joint embedding architectures is to generate representations that are invariant to augmentations. So again, we've seen that we want to be able to map this cat to the same embedding as this cat because it's fundamentally the same thing. And so the goal here of this pre-training task is to generate representations that are invariant to some augmentations. Whereas the goal for JEPA is to generate representations that are predictive of each other. So slightly different goals. And here we'll see that when we look at the results, but the computational costs for this approach tend to be high, whereas they tend to be low for the JEPA approach. And again, they share the same risk of representational collapse, but they solve it in a different way. Here we solve it by using both positive and negative examples. And here we solve it differently. I'll go over that in a second, but basically by not propagating the gradients through this encoder here. I'll detail that in a second. Okay, in going into a little more details. So again, we have an X and a Y. The X, so you have a picture, and to get your context block. So maybe I need to define the word block first. And before that, maybe I need to define token. So as you probably know, transformer-based approaches to computer vision typically divide an image into tokens, which are simply little squares, essentially. In this case, I think they use 16 pixels by 16 pixels squares, and they call that tokens. And a block is simply a set of contiguous tokens. So here you pick a context, which is just a block of tokens from your image. And there's only one. You only use a single context block. And on the target side of things, you encode the entire image, actually. But then in embedding space, you're going to mask the embeddings. You're going to mask some tokens. And so here you're going to use M target blocks. So they call them target blocks. The blue, red, and yellow blocks here would be M target blocks. But you mask them in embedding space. And then once you have your context encoder here, so you pass your context to your encoder, you get your encoder here. And then if you remember the little Z thing, so you're going to add to the context, the output of the context encoder, you're going to add the mask tokens and the positional encodings, and then that will go through your predictor. So the mask tokens and positional embeddings are represented here by this little thing. And actually the the arrow should point to this. So you add them to your context, and you independently for each target block, you're going to predict the target block here. Yeah, and then the distance that you're trying to minimize is the altitude distance between those two embeddings. And as I mentioned, this encoder here is not actually trained. It's simply you take the exponential moving average of the weights of the context encoder, and you make that the weights for your target encoder. So if you see here, you have f of theta bar, which is simply the moving average of f theta here in terms of weights. So the weights are not updated by gradient descents, and this is what avoids representational collapse. There's a lot of theoretical studies for why this works. I'm not going to go into those details. But yeah, basically, that's the high-level architecture. Here on the right of this slide, I have illustrated the context blocks and the target blocks. It's fairly straightforward. So basically, you pick a context block. In this case, it was this, like this, and then you pick your target blocks kind of randomly, and then you ensure that there's no overlap between your context block and your targets block. So you remove the overlapping parts from the context. And so now the task is from this context to predict those different parts of the images, non-overlapping parts of the image. That's basically the task. Any questions here?
Non-overlapping parts of the image, or the or the embeddings of those non-overlapping parts of the image?
The embedding, sorry, yes.
Right.
Everything is in embedding space. The prediction is happening in embedding space. That's the whole point of this.
Right.
Okay, if no more questions, I'll keep going. In terms of evaluation, I do a bunch of evaluations. In this slide, I present two of them, which is the frozen evaluation and the fine-tuning evaluation. What I mean by frozen evaluation is they freeze the backbone and then they fine-tune the linear head. And they do that on the ImageNet data sets. And for the fine-tuning evaluation, they either just fine-tune the linear head the same way as in the frozen evaluation, or they do full fine-tuning and they pick whatever is best. And they do that in a low shot setting, so they only fine-tune on 1% of ImageNet. Okay, so for the first one, the frozen evaluation, they compare their method to other methods that do not use data augmentation. So other either generative methods, other generative methods. So MAE, for instance, is well known, I think, by most people. And then the second section of this table is comparing it to some invariance-based methods, which typically will have a higher performance. But again, there are less general methods. So they compare different architectures. So here, basically, this column is the size of the model. Honestly, I don't actually know what BLH, those are like large, huge, or something like that. And then 16, I forgot, that's maybe the number of attention heads or something. It doesn't really matter. It's just bigger, essentially. And so here, ImageNet is a image classification problem. And basically, the results look pretty good for I-JEPA. And with the largest models, they actually become competitive with the invariance-based methods. I'm not going to spend too much time on the results because the V-JEPA paper from this year is even more impressive. I-JEPA is like cool and everything, but V-JEPA is even more impressive on a bunch of benchmarks. So I want to spend more time on the results for that paper. For this column, it basically shows that it performs really well in a low shot setting as well. And then this last row for this table is the comparison of compute costs, essentially, for the fine-tuning evaluation. They compare that to I-JEPA is one of the invariance-based methods. MAE is the generative method. Data to vec, not totally sure, remember which kind of method. I think it's a generative method as well. And so triangle here is the I-JEPA, the square is MAE, and then the circle is data to vec. And so if you look at the x-axis, which is the GPU hours or computational cost, and for each method, they have different model sizes. That's what these two triangles are, different model sizes. Same thing here, and same thing here. So across different model sizes, there's a fairly good trade-off between accuracy, which is the y-axis in this graph, and computational cost. And so you might think, when you compare the generative methods, oh, look, you have this encoder here, and you have to encode both the input and the target. That sounds like more computationally intensive than just, encoding the input. So maybe your expectation would be this feels more computationally expensive than this, and that's true. So you have extra compute from encoding the targets, but you have faster convergence. So if you look at the number of epochs here, it's much lower. And so overall, it leads to cheaper training.
So Cedric, another question. So if you go to the previous slide, this is evaluation data set, right? ImageNet 1K or 1% of ImageNet 1K. These are evaluation data set. The self-supervised training is happening on a different data set?
Yes. Yes, but it's also ImageNet.
Oh, it's also ImageNet. Is it ImageNet 21K or something?
I think it's ImageNet 1K.
Okay. But then does that sound fair? Like
all the methods are trained the same way, or pre-trained the same way.
Sounds good. Thank you.
And then here they look at different tasks, right? Not ImageNet. So that I think also addresses your question. So they call them high-level tasks and low-level tasks. High-level tasks would be image classification, and low-level tasks would be object counting and depth prediction. And this differentiation between a high-level task and low-level task, I think the point here is to determine how much your embeddings pay attention to detail, essentially. So for high-level tasks, again, you have a clear performance improvements compared to methods that do not use handcrafted data augmentation. So again, I'm just more going to focus on MAE because that's the most well-known. So significant improvement here. So these tasks, or CIFAR, I think is image classification. Places, I forgot, I have it somewhere here. Places, it's scene classification, and iNaturalist is fine grain recognition, or whatever that means, I forgot. And it's becoming competitive with some of the state-of-the-art methods that use handcrafted data augmentation. Again, I'm trying to spend more time on the V-JEPA results later. And again, here performs fairly well on low-level tasks, even though we expect ME to be better at this because they are forced to generate from their embeddings into pixel space, and the loss happens in pixel space and not in embedding space. And ME does perform better in both cases here. All right, now I want to talk about the same thing, but with videos. So that's the paper from this year, a couple of weeks ago, I think, actually. It's basically the same setup. So let's see. So the setup is the same. The only difference is that this input, which are tokens, so the tokens again are the little patches of an image. But here we're going to redefine token in a video context. So a token in this context is a 16 by 16 pixel block spanning 2 consecutive frames, as opposed to, well, I mean, obviously for an image, there is no notion of multiple frames. The temporal resolution of the video is we only select every 4 frames. And we use 3-second long video clips. So 3-second long video clips with only selecting every 4 frames. That means that the total number of frames you get is 16. And the spatial resolution is 224 pixels, and sometimes they use 384 pixels. I don't really know why. Okay, so the difference, it's actually the same. Right? There's no difference there, except, so you have tokens here. The tokens are just redefined to be this thing. And then you mask some tokens or you remove some, or you only keep certain tokens to get your context, your context. Sorry, let me rephrase this. So you see here this video here, and then you have the sort of grayed out tokens and the white tokens. I forgot which is which, doesn't matter. Basically, they select, actually I explain this better here. Let me explain the masking strategy in the next slide. But basically nothing has changed, it's the same idea. The way they do the masking strategy is, well, first, there's a challenge with video that does not exist with image, is that in video, there's a lot of information leakage due to spatial and temporal redundancy. So it makes it much easier than with a single image to have information leakage from, you know, the present or the future or the past. And so to avoid this sort of information leakage, you're going to mask a very large block that covers the full temporal dimension. So what that means is, if you look here, it's the same block over the entire 16 frames of the video. So they don't change from one frame to the other. It's the same mask. And it will cover on average 90% of the spatiotemporal tokens. And they use 2 types of masks, short-range masks and long-range masks. That simply mean, and then they do the union of all that. This simply means that they take 8 randomly sampled target blocks, and each of those blocks covers 15% of each frame. So if I go back here, for instance, this would be one block, this would be another block, and this would be yet another block. And you know, each correspond to approximately 15% of the entire image, and then they take the union of those. So that's the short-range masks. And on top of that, they also use 2 long-range masks, which are just larger blocks, essentially, that each cover 70% of the frame, of each frame. And the aspect ratio is just the shape of the mask that they use, whatever. They pick an aspect ratio from that range. And if you take the union of both short-range masks and long-range masks, on average, you're masking 90% of your video. And so the context block is basically everything that is not masked. So it would be the 10%, the remaining 10% here. Okay, hopefully that was clear. Stop me if that wasn't clear. What's their pre-training data?
Sorry, hi,
Yeah.
Cedric. I have one question about spatial resolution. Can you go back?
Yes.
So is this 224 blocks or pixels?
Pixels. Wait, now I'm suddenly hesitating. I think it's pixels.
Because
So
like
I
we
think this
have
just means
one block has 16 by 16, like 256 pixels, right?
yes. So
guess it
one block
should
is
be
16
blocks.
pixels. Say that again?
I'm just checking if it should be a single block or batch for this
Single
batch
block.
spatial resolution.
So each of these little guys here is a pixel block that is 16 by 16. So I assume the entire image is 224 by 224. And it's just divided into into tokens of 16 by 16.
Oh, okay. Okay.
Does that
Yeah, makes sense. Yep, thank you.
okay? Pre-training data, they created this data set they called video mix 2M for 2 million. And it's a mix of 3 publicly available data sets with these charming names. I'll go over what they actually are in a second. And so that's the pre-training data. Evaluation tasks. So you see that in the evaluation tasks, they reuse some of the data sets that are in the pre-training mix. So kinetics 400, something V2, are used both for pre-training and then for evaluation. But then they have other tasks that other data sets that are not used in pre-training. So AVA, ImageNet, Places, and Naturalist. And they use both video tasks and image tasks for evaluating the model. So Kinetics 400 is an action recognition dataset. And this dataset is mostly tests the appearance-based understanding of the model, because most of the actions in that dataset can be inferred from the presence of objects in the video. So it's mostly about whether you can understand the appearance of things in the video. Something V2 is a motion classification dataset, but in this case, the actions are not easily inferred from the appearances of specific objects in the video. So it tests more the temporal understanding of the model as opposed to the appearance-based understanding of the model. AVA is an action localization task. To be honest, I don't really know what that means. I assume it means in a video to figure out where some specific action is happening. And it tests the model's ability to understand and localize motions. ImageNet, everyone knows what the task here is. Places, and all these are classification tasks, essentially. Those are the same tasks that we looked at for I-JEPA. Okay, so again, the main point of this whole JEPA approach is to operate in representational space as opposed to pixel space. And so this table here, again, contrasts MAE-based approaches which are again in pixel prediction, and the JEPA approach, which is an embedding prediction. Okay, so this part of the table is about frozen evaluation. So again, you freeze the backbone and you do attention pooling here. I explain what attention pooling is in a second. And then fine tuning, you fine tune the whole thing, including the backbone. And K400 is kinetics 400, SSV2 is something V2, etc. Okay, so things to pay attention to in this table is the samples that are used, the number of samples used for, I forgot if it's pre-training now or I think it's before pre-training. So one thing to notice here is V-JEPA has seen less data. Is that right? I've forgotten now if it's pre-training data or fine-tuning data. It has to be pre-training because it's different data sets, yes. Okay, so this is the number of samples seen during pre-training. So fewer samples for JEPA, and the number of iterations of the model is also much lower, 90,000 iterations versus big numbers here. And V-JEPA sort of outperforms across the board almost compared to these other models. So things to pay attention to in particular is that here you see that OmniMAE outperforms V-JEPA on the ImageNet dataset. But that's mostly because OmniMAE is actually pre-trained on ImageNet. So we assume that that's the reason it outperforms V-JEPA. And even though V-JEPA has not been trained on ImageNet, it's like basically the same as OmniMAE. Okay, for the something V2, if you sort of look more carefully at the performance on the y-axis and the pre-training time or costs on the x-axis, you see that you have a much better trade-off for V-JEPA. So you have higher performance for lower cost, essentially, compared to video MAE. And if you go full fine-tuning and not just frozen evaluation with attention pooling, you have a similar conclusion, but here not in terms of cost, training cost, but in terms of data cost. So with less data, you have better performance, essentially. One quick note on what I mean by frozen evaluation with attention pooling is you have the frozen backbone, and then you add a head, essentially, and the head is this thing here. So you just use you fine-tune this part of the model for the frozen evaluation, and for the full end-to-end fine-tuning, you also fine-tune the backbone, not represented here. But this is the sort of the add-on for your domain adaptation. So you use a query, you train a query with cross-attention with the backbone output, and then you add up. So there's a residual connection between the query and the output of the cross-attention, MLP, layer norm, and then some linear classifier. And that's how they do what they call attentive probing. And that's how they get all these results. Okay. So that was comparing not necessarily to state-of-the-art models, but comparing to, it's basically this table is about comparing the effectiveness of pixel prediction versus representation prediction. But now, how does it compare to state-of-the-art models? So state-of-the-art models, you know, there are things like Dino V2, for instance, which are invariance-based methods using handcrafted data augmentation, but also the classic MAE stuff here. And so they also compare both on video tasks and on image tasks. And so these three models are model pre-trained on images, and those models are pre-trained on videos. And so they look at the performance of image-based models on video task, on both video task and image task, and video-based models on also both video task and image tasks. I know there's a lot going on in this table, but that's the basic idea. You have models trained on images only, or pre-trained on images only, and models pre-trained on videos only. And some of them are OmniMAE is trained both on, is pre-trained both on images and videos. Let's see. And this column data is the pre-training data that they used. Again, one thing to note is the number of parameters for V-JEPA is sort of on the low side here compared to these other models. And the performance is pretty good, if not the best in terms of video tasks. So it's the best across all models, except maybe this one here. And for image tasks, you would expect that image-based model would perform better on image tasks, which is what we are indeed seeing. So for instance, you have 86.2 here for Dino V2, which is an image-based model, versus 77.4 for V-JEPA. But again, V-JEPA is a video-based model, not an image-based model. So it's normal, it's expected that it would underperform on image tasks. However, I say we expect that. Maybe it's not obvious that we expect that. And actually, I think the authors in the paper say that maybe a reason why they're underperforming here is that the video mix 2M dataset, which is the video dataset that V-JEPA is trained on, lacks the visual diversity of the internet scale pre-training data used by image models. So basically what they're saying is models that are pre-trained on images have an advantage because the datasets, the pre-training datasets that are image-based are way more diverse and big than the video data that we can pre-train on. And so that hurts the video-based models. Nonetheless, V-JEPA sort of closes the gap between other video-based models and image-based models for image tasks. Hopefully that was clear. There's a lot of video and image stuff, but hopefully you get the main point here. Okay, I think, let's see. Okay, I have only 2 more slides. Label efficiency. The message here is fairly straightforward. So they look at 2 data sets, the Kinetics 400 and something V2 data sets, which again are motion or action classification data sets or tasks. And they compare V-JEPA to MAE again. And what they do here is for a given model size, they look at frozen evaluation with less and less labels. So you fine tune on less and less labels. And what they find is that the performance gap, so they're basically V-JEPA outperforms for all, so the more you go to the left, the fewer shots you have essentially. So the fewer, for every sort of level of shots, V-JEPA outperforms the other models, but the performance gap between the two increases as the number of shots decreases. So basically, the less you see data, the bigger the gap between V-JEPA and the other models. Of course, the more shots you have, the smaller the performance gap. But this basically means that V-JEPA is really good at learning or at adapting with very little data. So that's a pretty important message. And that's true for both data sets or both tasks, essentially, Kinetics 400 and something V2. Okay, I wanted to conclude with what can we use that? So there's 3 main takeaways here. One is JEPAs are modality agnostic. So the same method, meaning embedding prediction, can be used to pre-train either a point cloud backbone or an image backbone, because it all operates in embedding space, essentially. So all you need is some encoder, and then you're good to go. You do embedding prediction in that embedding space. So it's the same method can be used with different modalities. JEPAs have good performance in frozen evaluation. So that's another takeaway. And how could we use that? We could use that by freezing a large backbone and only train an attentive probe. Again, if you remember, the attentive probe was this little guy. So a simple head on top of your model during a release cycle. And because it performs really well with, not a ton of data, you could, well, actually, that's not really the point of this takeaway here. Basically, the idea here is you can freeze your backbone. You don't need to fine tune your backbone over and over again. And so that makes your development or your release cycle much faster because you don't need to retrain your entire backbone. Speeds up development, reduces cost. The third takeaway is that JEPAs are data and label efficient. So that's the point I was just making here. So you can fine tune your backbone with relatively a small amount of data and still get really good performance. So yeah, speeds up development and reduces cost. So I think all these takeaways are things we could take advantage of. And so yeah, food for thought.